Testing. Testing, testing. Testing, 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 testing. Testing, 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 testing. Does it work? Does it test? Will it fly? Does it work? Does it test? Alright. Just seemed to work. Let's see if we can get the audio to work as well. How's it going, Daily? Or you can barely hear that audio. That's not good. See if I make it way louder. Barely hear that audio. That's not good. See if I make it way louder. You can kind of hear it a little bit better, but I don't know, still hard to see. How we're gonna do this? All right. Kind of hear it a little bit better, but I don't know, still hard to see. Do this. All right. All right, we're gonna try not to do too many audio critique. Just try to get some more exploration done here. How's it going, Ed? How's it going, Crushed Keys? All right, so today we're going to be looking at the AudioCraft GitHub repo. So this is a GitHub repo coming out of Facebook Research. This is actually the official GitHub repo for a couple different papers. And I think we've actually read some of these papers. I think we definitely read MusicGen, and then we might have read some of these other papers. I honestly don't even recall anymore. But they sound familiar. I feel like I definitely read this one. Maybe not this one. MusicGen. I read one that had like a kind of like a rainbow on the front. I can only remember the pictures, but basically it's generating audio from text descriptions. It's conditional audio generation, and you can condition it on a variety of things. And yeah, that's basically it. So first thing you want to look at when you, this is actually my fork of the repo. I want the official repo. So I created a fork of this repo so we could mess with it. But yeah, first thing you want to look at when you see this repo, you want to look at the stars. So 14,000 stars, that's definitely popular. You want to look at the license, for example, here, MIT license, which is pretty good. It means you can use it, and you can use it for products as well. Unfortunately, if you scroll down further, the code is an MIT license, which means you can use this code in your startup product, but the model weights are CC by NC, which is non-commercial. So unfortunately, this is actually fake open source, where the code is open sourced, but then the model weights themselves are not open source. So you can't actually use this for a commercial use case. Does it use some equivalent of music equivalent of clip or something? So it's not, I don't know exactly what it's using for the text. I assume there's probably something like that. I forget, but there's probably some data set that has text descriptions and then audio, and then it basically just creates some latent space where you can basically project text, find the audio or something like that. But I think the main kind of cool thing that they have here is their encoder, which is this encodec, I'm pretty sure. It's audio encoder. It's basically, it's generating audio token by token, but the tokens are audio tokens, and those audio tokens are the result of this audio encoder. Okay, but going back. So we were looking at this repo, we saw the license, We saw that the license is CC by NC for the saved weights, which is a little bit unfortunate, but other than that, relatively clean here. We have some installation instructions. They're actually not complete. I actually did have to install a bunch of other crap on my computer before I could even get this running this morning. But yeah, so far so good. We got a lot of usage here, a lot of contributors here. Another thing I like to do is go into this insights page, and then you can look at the contributors, the commits, the frequency. You can kind of check out who's actually committing stuff here. You know, sometimes these take a second to load. Whoever is working at GitHub, if you guys can get these to work faster, I don't know why they are so slow, but if you fine-tune the weights, can you use them for commercial use, or would you need to train them from scratch? I think if you fine-tune the weights, you'd probably could get sued. But I think that the important thing to realize here is that there's not... It's not like as obvious as you think it is. It's more like they're going to sue you regardless. So that's another way to think about it. In the tech world, once you get to a certain size, you're just going to get sued, and they're going to find a reason to sue you. So you could be using this for your startup just with the weights that exist, and you use it for years, and then only after you start getting to a certain scale, Facebook will have people look into ways of how to sue you, and they can figure out how to, okay, maybe if you're fine-tuning on them, then we can sue you or something like that. But it's not entirely clear, right? Because you can imagine someone taking kind of what they did in Vicuña, right? So they took a llama model and then they fine-tuned the llama model on the output from GPT. So what's the legality of that, right? What's the legality of taking an output from a Vicuña model and then training something, distilling a model from that, right? So I think the legal world doesn't really know what to do yet about this, like fine-tuning and then fine-tuning on the output of some other thing that is open source, but this other thing isn't open source, and then it's getting very complicated very quickly. So I think the rule of thumb is until your startup is big enough that it matters, you're not going to get sued. So, you know, it's kind of the same thing. If you're growing one weed plant or 2 weed plants, you're not going to get arrested by the police. But if you're growing 100 weed plants, they're going to come to your house. So I think it's the same thing. It's going to come down to how much money you have, how much money you're making. All right, so we see the main contributors here are A. Defosse, which I think is one of the paper authors, did most of the contributions. Then you have this other person here, Jade Coppett, kind of seems like took over afterwards. So this was all the main contributing, and then most of it happened here at the end. You see people here contributing near the end, and then some people at the beginning. So who is this Jade Coppett? Jade Coppett works at Facebook Research. Okay, so basically this is the original author, and then this person took over and now maintains this repo. Because I also noticed that if you actually look at the documentation, all the documentation, a lot of it at least, was added or edited by this Jade Coppett person. So Jade is the first author on the paper. Okay. Which paper should I be looking at? Is it the MusicGen paper? Is this the main paper? Music LM. That's not the right paper. That's why I was confused. There's another AudioGen. Let's see. MusicGen paper. Simple and controllable music paper. Yeah, it is. There you go. You're right. Jade Coppett, first author. Okay, wait. I think I know what's going on here. Okay, so what if AudioCraft is an older repo that then got added later? I bet you that's what happened. There was an older GitHub repo, which was created by this original dude, and then where is it? Commit activity, contributors. Yeah, maybe this person wrote an original paper and then this Jade Coppet person took it over and then added stuff and created this new paper. So we're talking about a GitHub repo that has associated for a variety of papers. Let's look at this one, AudioGen. When was this released? 2022, and then this one is 2023. Yeah, so we're talking. It seems like it's like a whole. There we go. Here's this Alexander Defosse guy, who's the main contributor here. Okay. So now we're getting an idea. It's basically there's multiple years of work, multiple different papers, multiple people contributing into this over time, which is why it's generally a pretty clean repo. Okay. This is big. Is it big? I think it's pretty big. So what else? So I had to install some NVIDIA stuff. Let me just get this out of the way here. NVIDIA installation. This stuff is always super annoying. Getting the CUDA version. There are no changes stage to commit cancel. All right. But I also had to download some models which are available on Hugging Face. They have a couple different sizes too. There's a AudioGen medium, AudioGen small. Let's see if I can find it. And then MusicGen medium and MusicGen small. So you can download them directly from here, or you can use this Hugging Face hub that I found, where basically you can do this Hugging Face hub snapshot download, and that allows you to download them as well. So I'm going to be using the small models for today just because they're faster and because the GPU on this machine is shite. So there's a couple examples in this GitHub repo. So if we actually go to this inside the demos, here's where one of the first things you always kind of want to look at. They have a Python notebook. So all right, that's pretty good. And then you have a MusicGen demo, AudioGen demo. So, and then a MusicGen app. And I think the MusicGen app is a grad.io app, right? So I bet you this is the same app that you would get here in the MusicGen space on Hugging Face. So Python demos MusicGen app. Let's see. And then we can control click on that, and here we go. All right, so this is running locally versus this is the app that is running on Hugging Face. So we can see that the one that runs locally is actually a little bit more fully featured here. So I don't know, let's try to figure out how this works. So input text, a cat meow, condition on a melody optional file. No, I don't really want to condition on a melody. I just want to condition on only the text. So I think MusicGen small, medium, large, and then melody. Melody is probably the one that can condition on a melody. We just want conditioning on the text. Let's hit submit. It's doing something. Is it logging over here? Oh no, we're already getting CUDA out of memory errors. I think it's because I have this open. Let me clear all outputs, restart, save, close. Okay, it errored out of memory. Let me Control-Shift-T, open up a new tab here, go to NVIDIA SMI. Actually, even better than that. Let's close this out. Let's open up a new terminal. Let's watch-n. Every, let's say, 0.1 seconds, NVIDIA SMI, and this will be useful so we can see how much memory usage is happening from this GPU. So on this computer, I have a 3060, something like that, 3060 with 12 gigs of memory, kind of an older GPU, but it still checks out. And let's see. So let's click this submit button again. All right, so we see here the GPU memory going up, going up, going up, going up, going up. Kind of hovers around 5 gigs. And that's it. So okay, kind of maxed out at around 6 gigs. We see here that it stays at the 6 gigs, which means that the model is still loaded. So keeps the model loaded. And we finally have the generated music, which was conditioned on this text here, cat meow. So let's hear it. Okay, that doesn't sound anything like a cat meow. Let's see. Okay, maybe it's not good at like automatopoeia kind of sounds or something. A lullaby. Is that how you spell lullaby? Lullaby. A lullaby. Lullaby. For babies with cat sounds. Meow. Meows. Alright, let's submit that. Alright, we see how the memory here no longer changes on our GPU because the model's already been loaded. So that's why the memory is constant. Now, okay, let's see if this is any better. It's a little bit haunting, but at least it's very much a lullaby, right? That does sound completely different than before, so I think the keyword there was probably lullaby. And this is maybe an interesting thing to think about, where in image generation models, right, diffusion models, the shared space between text and images is very rich. So pretty much every single word that you can think of, there's been some training examples in the image data set of images that correspond to that word, right? So there's a richness to that latent space between text and images. But I think when you're doing audio, I bet you it's probably not as rich. I bet you that a lot of words don't appear in the training data set, right? Like, seems like this word meow doesn't appear into it, right? And if you put something like this, partial differential equations, or like I don't know, let's do the orange color of an orangutan. You know, like, I don't think that's ever appeared in this training corpus, so it's like it's probably going to sound like complete garbage here, versus if you put this into an image generation model, it would get something a lot better. Yeah, it just sounds like noise. Okay. All right, so we got the model, we got a decoder, and we got a duration. Okay, so duration is just the duration here. Multiband diffusion versus default. So I don't know what the fuck that is, so we're going to come here into this repo, and we're going to search for multiband diffusion. Class multiband diffusion. Let me see if I can just search and I can find it in the AudioCraft in the README. Here we go. Improving multiband diffusion performance. Add multiband diffusion option to MusicGen. Okay, so this is the when they actually added it. So in August 8th, it's actually one of the latest things that they added. So generally, the latest things are going to be the better things. Let's see what that actually ends up looking like. Okay, multiband diffusion. We're going to click on that. Let's try to generate the same orangutan situation going on. Or maybe even better, alien invasion sound. Yeah, that's probably what it sounds like. Lullaby of cat meows. This is taking much longer. It's still the same amount of memory, so it doesn't seem like the multiband diffusion has necessarily done much here. TTS generation, that's not what I want. AudioCraft docs. AudioGen. See if we can find diffusion in here. Multiband. Multiband, nope. Alright, let's go back to our Is this done generating? Still not done. Something's going on. Let's turn the duration down. Let's do something like 5 here. Submit. Interrupt. Might have to kill it and restart it. Let's kill it and restart it. Oh, it's because it's downloading. Here you go. It's downloading a model. That's why it's taking forever. Let's Control C out of that. Let's rerun it. Let's refresh. Refresh. Multiband diffusion, input text, lullaby with cat meows. Submit. All right, let's see over here. Okay, so it has to download the MDB MusicGen 32 kilohertz multiband diffusion. Here we go. Maybe they describe it here. Sample from multiple diffusion models. args, DP, list of diffusion processes, and a compression model. So it takes a list of diffusion processes, TP list. This is kind of cool. So this is a subject or a pattern that I see in this repo where a lot of times when I, let's say, create a, let's say you created a list here, right? A is a list. 1, 2, 3, like that. I generally, the way I would import this is I would say from typing, oh my god, import list, like that. But in this repo, the way that they're doing it is they're doing it like this: import typing as TP, and then they do tp.list. So it's kind of a cool little convention. You know, I'm a huge fan of weird little Python syntax like that. So I thought that was kind of cool that they did that. So you don't have to basically have this giant import statement at the top. You can basically just do that. Okay, so what are we doing here? We're get MDB MusicGen. This is the download path that it's downloading from here. Right. Load compression, load diffusion model, creates a noise schedule, and then appends this noise schedule for the range and length models. And the amount of models comes from where? It comes from here, load diffusion model. So you just have one model. What is this doing? Load diffusion model. Get diffusion model, processor models, .append model. Okay, so it's loading two different things here. It's loading this diffusion model and then also this processor. What is this? Sample processor, multiband processor. Project original sample to the space where diffusion will happen. Return back. So now we're finally in a torch module that gets and receives tensors multiband processor. The input audio is splitted across frequency bands, evenly distributed in the MEL scale. Okay. So the MEL scale is a commonly used for spectrograms, but it's basically an audio scale that is based on human hearing. It's a scale of pitches judged by listeners to be equal in distance. So it's a human-based scale. And human hearing doesn't go up in a normal linear way. It kind of goes up in a weird pattern. I think the loudness is also the same. 1420, 1500. So these are the actual frequencies here of the MEL scale. Okay. Each band will be rescaled to match the power distribution of Gaussian noise in that band using online metrics computed on the first few steps. Number of MEL bands. By default, this is 8. The default sample rate is 2400. Seems pretty standard. Actually, that's not standard. I think 16 kilohertz is something that I see, and I also see 44 kilohertz a lot, but 24 kilohertz is a little weird. Tested this model yesterday. Honestly, a bit disappointing. Lol. It's hard to reproduce the quality of their demo. Yeah, so they're probably cherry picked. That's the one thing that we're kind of starting to realize here, is that these aren't as good. So now we use the multiband diffusion decoder, and this, I guess this is the original. Okay, very lullaby-like, but kind of disturbing, and also doesn't really have meows. You can almost feel like it's starting to have a meow there, but it's not quite. And let's look at this. These sound so weird. Like there's just like some kind of weird, like piercing effect in that, you know? Like it almost like it needs equalized. We need like an audio engineer to tell us what's wrong with that. It sounds like it's like just not balanced correctly. Okay. Power SDD rescaling factor. The power of Gaussian noise in each band is taken to that power, so maybe we could actually balance it by messing with this, to be honest, but okay. What else is there here that we can look at? Top K, top P, temperature, and classifier free guidance. So the reason these are hyperparameters that you generally see with a language model, and the reason that they're relevant here is because I think MusicGen is actually treating this as if it was a language generation task, right? So it's basically generating these tokens based on the previous tokens, much like a language model generates tokens based on the previous tokens, right? Autoregressive creation of these tokens. But in this case, their tokens are encoded music tokens instead of text tokens. So that's why you can have top P, temperature, classifier free, and so on. Let's actually see what we get if we put a temperature of 0 here. Let's do default, submit. I'm curious what the 0 temperature lullaby with cat meows sounds like. That's the last sound you hear before the aliens explode your brain. Okay. Let's close that. Let's close this. Let's close this. And this is just the pared down. I think they have some demos here. Let's see what their demos are like. So this is one of the examples. A cheerful country song with acoustic guitars. That's not at all the right audio file. That's like a colonial like flute song. Where's the guitar, right? That's what I'm thinking. I think actually no, I understand what's going on here. This is not the actual output. This is a melody file, so you can condition on a melody. The same way that you can condition on the text, you can condition on a melody, and then it should create a cheerful country song with acoustic guitars that has this melody. So actually, why don't we download this melody here, rerun our model here. It looks like the model's still loaded. It's around 10 gigs now to load this. Let's do file. We're going to upload this Bolero Ravel that we just took, right? This is the... And now let's see if we can generate the lullaby with cat meows from that. All right, so now we're conditioning on this text, and we're also conditioning on this melody. Let's see, should be the same. So let's hear this once more, just to get an idea of the melody. It's like ma na 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 na. So, I mean, that definitely is the same melody, so it the conditional generation did match the melody, but it kind of completely far away from this. What do we do? This metal song with cat meows. It might be the case that the melody conditioning kind of overrides the text or is a lot stronger, so you would basically need to edit this classifier free guidance. I don't know. This is one of many different types of hyperparameters that allow you to kind of determine the strength of the conditioning, but here I don't know what it refers to. I don't know if it refers to just the strength of this or just the strength of that or the strength of this relative to that. What is that? That sounds terrible. Okay. Okay. So we've explored the little repo here, or the little demo. What else can we do here? So in the docs, they actually have very nice docs. Let's look at the conditioning. So modular implementation of conditioning modules. Okay, so modular means that you can basically change it as you want. You've got WAV conditioning. WAV is a type of audio file, so this basically means a WAV file with a specific length, a specific sample rate, and a specific path to that. You see here the typing convention or syntax that they have with the tp.list. And seek time, I don't know what that's going to be used for. And then you have joint embed conditioner. So I guess here you go. Here's if you have both text and WAV, that joins them together into one conditioning. Text attributes, WAV attributes. To flat dictionary, this just flattens out. So here they're unpacking these dictionaries, probably used for config from flat dictionary. This is like, so you could give this this class method as a way to create the class. So you see how here it's creating an instance of itself and then basically initializing all the attributes with whatever this dictionary you gave it. So you can initialize these conditioning attribute objects from dictionaries. Damn, you guys are popping off here. It would be interesting to train a model on a MIDI format that directly includes musical notes. I think I've seen that before. I don't know where, but I feel like that's definitely a thing. Conditioning on MIDI. Masked autoencoding on a transformer that processes MIDI beats would be fun. Yes, MIDI is basically the kind of like more like piano keys. Like sometimes when you see people producing music and you MIDI production music. Yeah, like here you'll. No, I mean, that's not what I'm looking for. Where is it? This is not MIDI, right? This is actual raw audio waveforms. But sometimes you'll see this, kind of, no. MIDI production music, Fruity Loops. That's how old my music production knowledge is. Is this MIDI? No, this is still just raw waveforms. I'm never going to get a good picture of, this is MIDI, here we go. So this is what a MIDI file looks like, right? And I guess what you guys are asking is why can't we condition the music generation on this type of stuff, right? It's kind of like piano key equivalent. Here's more pictures of MIDI files. And the MIDI file would be basically this, but in file format. Okay, so that's that. Segment with attributes. Base class for all data classes that are used for conditioning. All child classes should implement 2 condition attributes that convert the existing attributes of a data class to a conditioning attribute. Okay, so you have a little bit of a conversion happening here. What is this segment info? Import segment info from audio dataset. Okay, why don't we actually look at their audio dataset format? Our dataset manifest file consists in one JSON per line, potentially gzipped. Do they have an example? Use the example dataset provided under the dataset folder. Go to the dataset folder. Here we go. electro1.json and then electro1.mp3. So this is probably the metadata for this MP3 file here. Let's see. So you have key, artist, sample rate, MP3 file extension, description. Here's the actual text. I guess maybe they also have keywords. That's kind of interesting. They're breaking up the text into two different kind of higher or categories here. So you have something called the description and something called the keyword. I wonder if you could use this here in our actual generation. Metal song with cat meows, bright, pulsing, cool. And what else? Duration 15 beats per minute. Don't even have the beats per minute. So it seems like you can have empty values here for some of these keys. And electronic enracinement. I guess that's just the name of the song. So uplifting, more moods. It's kind of interesting. Why don't they give us the ability to condition on more than just the mood, or more than just, right? Shouldn't they break that up? Oh my god, dude, this is so jarring. Okay. I think it might also be because I'm literally blasting this through my monitor speakers. See the example in the uses a example dataset provided. Manifest files are stored in the EGS folder. Once you create a manifest file for each of the splits and specify the correct path to the given manifest file. Creating manifest files. Do they have one here? Let's see. So in the data folder, not in the data folder, in the data sets folder, right here. I think the manifest file is just that. Configuration folder. Okay, so you actually have to define it in a config folder. Where's that? Let's go to the config folder. I don't know the result though. They don't release it officially. Seems like it's the author's side project. This is a diffusion model, so it can be conditioned on anything. Yeah, Christopher. So I think what they're doing here, at least with the conditioning part, conditioners, is that you can condition on any combination of things. So you could probably actually add your own condition, make your own conditioner, condition on emojis. Actually, why don't we do that? Why don't we actually see what emoji? Cat emoji. Not mcat, just cat. Here we go. Cat face emoji. Copy. Paste. Get rid of this. Only use MusicGen small. Submit. Still has it loaded in memory. That's no good. It should have cleared the memory. You know, you don't want to have things loaded that you don't need to. Okay, so this is literally cat emoji. I feel like I can hear like almost like metal drums in that. Config dset dataset config audio default. Okay, so this is what your dataset config would look like. Okay. I think one thing maybe we can try to do today is actually see if we can run the fine tuning. Max sample rate, max channels, EGS, music caps. So this is the different data sets. Audio caps 16, music caps 32. Sample rate, channels. Okay. And this is the example. Max sample rate 48,000. That's actually different than what we saw in the data set. That's a little weird. Okay. Creating manifest files, music dataset, metadata. Okay. Is there a training here? Training. Training pipelines are built on top of PyTorch as our core deep learning library, flashy. About epochs, models, conditioners, configuration, running experiments, launching jobs. Dora is experiment manager tool. What is this? Facebook Dora. Dora the Explorer friendly experiment manager. So experiment manager is something like a Tensorboard or a weights and biases. Those are some common experiment managers. But I guess this is Facebook's internal experiment manager. It does grid search, so you can search through some hyperparameters. Okay, I don't want to necessarily have to deal with that. Is there training that I can just run on a single thing without? Maybe MusicGen. Model card, usage. Run the grad.io demo locally. That's what we did. Play the MusicGen demo. Okay. I think that's probably just going to be the grad.io demo. Recommend 16 gigabytes of memory. Unfortunately, we do not have that. We just have 12. Quick example. MusicGen melody, set generation, generate unconditional, generate torch audio.load, generate with chroma. Okay, transformers if you wanted to use Hugging Face, but that's not what we're doing. Okay, here we go. Training. Implements MusicGen's training pipeline. Defines an autoregressive language modeling task, right? So it's basically generating this audio as if it was a language, or as if it was text, over multiple streams of discrete tokens extracted from a pre-trained encodec model. And this is their encoder. Okay, so it's kind of analogous to how you're doing diffusion in a latent space. Here you're doing generation of music in this encoded audio token space. Do not provide any data sets. We provide a dummy data set. In particular, the environment setup. Let's ignore that, and then we'll eventually realize we have to go back to it. MusicGen base model for text to music. Dry run init. It's probably not even going to work because we don't have Dora installed. Let's see. Let's actually have this maxed out like that. Control Z. Kill %1. All right. Is this still using our GPU? No. You see, we're free. It's officially dead. Sometimes those Python zombie processes can consume your GPU, so you have to be careful. All right, let's try to just vanilla copy paste this. For sure it's not going to work, so let's see. It's probably going to say doesn't know what Dora is. Oh shit, no, it does work. It does have Dora. Dora help. It must have installed it when I installed this repo. Okay. Package training module. Main module, training exec name. Dora will search for this module to run within the package, and then verbose. So why don't we do that? Why don't we Dora grid. Let's do Dora /v -v. So it's verbose. Unknown argument -v -- verbose. What? Come on. Come on. MusicGen base 32 kilohertz. Dataset internal music 4000. So, okay, so this is obviously not going to work because we don't have the internal dataset. Autocast false. FSD, I think this is the parallel. Train. I can't read this because it's configured so poorly. Okay, here we go. Train valid. Name. Remove the -- dry run to actually schedule the jobs once everything is in setup. Okay, we're probably going to need to use a different data set here. Let's do this. This is the solver. Okay, so the solver is basically a config file. Defaults, LM, override, float 16. Batch size. Definitely gonna have to do way less than that. Okay, so why don't we make our own solver? Let's come here. Let's close out of all this crap. Don't save. Control KW closes out of all of that. Where is this solver? Here, this solver is in config solver MusicGen. So go to config, AudioCraft, config, solver, MusicGen, default, debug. This sounds like more like what we want here. Let's try that one. Verbose grid MusicGen base 32 kilohertz. Let's do MusicGen dot debug. Dry run. No grid file MusicGen dash debug. So it's looking for a specific grids. MusicGen base cache pre-trained 32 kilohertz, base cached. This one. AudioCraft environment. Jesus, where are we going here? Slurm launcher. That's not what we want. Slurm is a cluster kind of management software. So if you have a bunch of computers, a lot of academic institutions use Slurm, to be honest. Okay, so these are not going to be good because these are all just launch files for specific Slurm clusters, of which we do not have. All right, let's go back. Let's go back. We've gone too deep in the wrong direction. Not provide any of the data sets. Provide configurations. MusicGen solver equals this. This is grids. That's not what we want. Music dataset metadata. Underlying dataset augmented music specific dataset. Audio tokenizer. Couple of audio tokenizers, so you can use their pre-trained encodec model, DAC, which I think is discrete audio. What is this? No, descript audio codec, so a different audio codec. Is this one also neural networks based? Yeah, this is also weights are released, so some other encoder audio codec that uses deep learning. The tokenizer is controlled with the setting compression model checkpoint. Using your own model. Fine-tuning existing models. All right, finally we got to it. Kind of got a little distracted there with the training, but now here, this is probably what we want. You can initialize your model to one of the pre-trained models by using the continue from argument. Okay, so Dora run solver equals this, model equals that, continue from pre-trained Facebook, medium conditioner, text to music, MusicGen medium. You are responsible for selecting the other parameters accordingly in a way that makes it compatible with the model you are fine-tuning. Configuration is not automatically inherited from the model you continue from. In particular, make sure to select the proper conditioner and model LM model scale. Using another model you have already trained. Let's try to just do this first one here. Let's come here. Let's put that in there. It's not going to work, but let's see. Missing mandatory value, data source dot evaluate. Okay, so we're missing specific config values here. The solver is MusicGen base. So that's the thing that I think we were trying to mess with here. This solver, MusicGen solver, eval solver. If we search in here for data source.evaluate, data source.evaluate, evaluate. So it's looking in the config object here. Data loaders evaluate. This is probably where it fails. Should run eval. What if we don't run eval? Can we skip this error? Also, let's take this and write it in a little bit of a nicer way here. So I have my little script here. Let's also make a new script. Make a new file here. We're going to call it finetune.sh. I'll put this here. And we're just going to split these quarks a little bit, just so it's easier for us to see what the fuck is going on here. Model scale medium. Continue from medium. And also, we need to choose a small model scale because we're not going to be able to do the big one for sure. Okay. And then conditioner text to music. All right, let's see over here if there's any difference here. Continue from sig conditioner text to music. Continue from a checkpoint if you want a specific checkpoint. Conditioner model scale. Those are both set. That's fine. Slightly different layers. If you decide to change some parts like conditioning or some other parts of the model, you're responsible for manually crafting a checkpoint file from which we can safely run load state dict. Okay. So this seems like it should be fine. Let's actually run that. See what we get. Okay, so where is this failing? So it's failing because it doesn't have this data source.evaluate. And where does it want that data source.evaluate? It's running, then it's running this Dora, then it's using Dora, still in Dora, still in Dora. The problem is not going to be in Dora. The problem is going to be in OmegaConf, which is the config management. Okay, so Dora uses OmegaConf. Go deeper, 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 deeper here, and then when it actually fails here, missing mandatory value data source.evaluate. Let's see if we can find this data source.evaluate in the repo. Let's go to our repo, Control Shift F. We're going to search for data source.evaluate. Does not exist. Let's look over here. Let's use AudioCraft. Here we go. Go to the top, page up. Search in this repo. We're going to search for data source.evaluate. Does not exist. Damn. All right. Can we maybe just data source? Manifest files consists in one JSON then provided in the configuration as a data source subconfiguration. Config data source key. Dset. Okay, so the data source is the dataset config value, of which here's the default. So whatever we're using does not contain anything here, basically, is the problem. So I bet you if we go and we look at the audio music caps, is it this one? Is this the one we're using? EGS music caps. What is the dataset config that we're using? MusicGen base 32K hertz audio. It's not music caps. What we want is MusicGen. Internal. This. I don't even know what. Let's go back. Let's go back. We've gone too deep. So remember here at the beginning when they said read the training documentation. We're going to go back and we're going to read this training documentation. Team and cluster configuration. Conda env config AudioCraft team. I don't think we need that. Train new models. We just want fine tuning. What's going on, Luke? Each task supported has its own training pipeline and dedicated solver. That's good. I want to know how to get the solver. Learn more about solvers and key design around AudioCraft pipeline. The core training component in AudioCraft is the solver. A solver holds the definition of how to solve a given task. It implements the training pipeline logic, combines the dataset, model, blah, 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 into the full training loop. We refer to the reader to Flashy. What the fuck is this? What is Flashy? Another internal Facebook tool. Okay, so we learned about Dora, which is Facebook's experiment management and logger kind of tool, experiment tracker. And now we're learning about Flashy. So Flashy is the solver. Okay. PyTorch Lightning, vastly over-engineered. Flashy aims to be an alternative. Okay, so it's basically PyTorch Lightning, but Meta's own version of that. You can use it without Flashy. Logging metrics to multiple backends. That's a weird way to spell wandb. Checkpointing and automatically tracking stateful part of the solver. Beyond those core features, Flashy also provides distributed training utilities, which we don't need, in particular alternatives to distributed data parallel, which we don't need because we're just trying to fine-tune on a single GPU here. Each epoch, you're going to need to do train, valid, and test. Maybe if we get rid of the eval, then it won't fail on this can't load the eval. Okay, that's a possible hypothesis. Let's keep going. AudioCraft has an initial solver, the standard solver. The standard solver provides a nice base management of logging, checkpoints, restoration. Make the assumption that all tasks are following the same set of stages: train, valid, eval, and generate, each relying on a dedicated dataset. Okay, each solver is responsible for defining the task and associated stages in order to leave full ownership of the training pipeline to the researchers. This includes loading the datasets, building the model and optimization components, registering them, and defining the execution of each stage. To create a new solver, one should extend the standard solver and define each stage of the training loop. We probably don't need to make our own solver. There's probably already a solver that we can use. It's just that we're not passing it the full dictionary configuration that it needs, this omega conf dict config. Okay. Run step, train, valid, evaluate, generate. AudioCraft uses the concept of epoch, which is basically just one pass over the whole data set, but instead represents the smallest amount of computation that we want to work with before checkpointing. That's kind of an interesting definition for epoch. Like, this is the formal definition of what one epoch is, but here they're basically saying it's some amount of computation that you're going to run before a checkpoint. It's kind of an interesting way to think about it. An epoch time around 30 minutes is ideal in terms of both safety and getting updates. Okay. Updates per epoch. And you can control how long the valid takes with num samples. Other stages, such as evaluate and generate, will only happen every X epochs. Model is a container object which wraps one or two or more torch modules together. The model wraps the encoder, a quantization bottleneck module, a decoder, and some tensor processing logic. Okay. Configuration. We're getting close. I feel like we're close here. It relies on Hydra. The concept of configs and structure. Updating the root default will have an impact. One should never change the default configuration files. Instead, they should use Hydra config groups in order to store custom configuration. Dude, fuck it. I can't wait until language models do all the config management for us. You know, the amount of time it's been spent wasted on these config management tools and learning all these different configs and dealing with config issues. Conditioner, dset, solver, model, team. So is that kind of corresponding to what we have here? Solver. Continue from. Maybe we just need to say dset equals something. Dora run solver equals this. Let's go back to our fine tuning. Docs, MusicGen. At the bottom here, they had the fine tuning, playing with the model, importing, learning more, citation. Importing, exporting models. Easily get access to the solver with the latest trained model using this. Listening to samples. Generation stage. Evaluate. Solver MusicGen evaluation objective eval. Is that what we want? Can we just get rid of the eval here? Fine tuning. Currently do not support caching of encodec evaluation. Also computing. What if we do this? Let's add that to our little script here. Okay. So we're adding this extra solver to our config. See if that gets rid of the crap. No, it still wants that. Oh my god. Alright, well, you know, if you're not going to play nice, AudioGen, what the fuck is going on? Why are you going to annoy us like that? Download model. There should be a dataset config. Is I think what's going on. This one? No, that's not what I want. I want MusicGen, solver, MusicGen, evaluation, none, objective eval, text evaluate. Is this, are we finally there? Is that it? Let me actually close this as well, just so we don't have that messing with us. Data source dot evaluate. Dataset dot evaluate. Ooh, so close. Dataset evaluate. We want data source evaluate. Data source evaluate. That's what we want. Default. Data source evaluate. Example. How do I use this exact file here? Can I just copy this? Data source dash evaluate. Oh, data source slash evaluate. And I'm going to set that equal to, what do they set it equal to? The example, EGS dash example. Let's try that. All right. It's going to fail on a different thing here. Could not override data source dot evaluate. To append to your config, use plus data source dot evaluate dash example. Okay. Let's bring this down here. And we'll do this plus. All right, so now we've added the data source dash evaluate, and now it's saying I can't find it. I gave it to you. What do you mean you can't find it? Oh my God. All right. The above exception caused the following exception. Cannot override. I need dash verbose. I think that's the problem. I think if I had dash dash verbose, maybe it would actually tell me what it's using. So let's come here. Let's add this verbose flag so that we can actually, hopefully it tells us where it's getting this config file, because we still don't actually know where the fuck this config file is. Unrecognized arguments dash dash verbose. The verbose needs to happen before the run. That's what I'm learning. Okay, so now let's scroll. Dora directory dash temp dash AudioCraft oop. Oop is the name of the user on this computer. All right. Config loader. I wish I could just know what config file it's using, right? Wouldn't that be super helpful if it actually told you what config file it was using? MusicGen debug. Maybe it's because we're using the MusicGen debug. Let's try to use MusicGen base 32 kilohertz. No, that's what it's using. Let's do this. Let's get rid of that. Put that there. And let's also make a version of this that has the debug. See if we can at least get this one. Can we get it? All right, there we go. Look at that. It's working. Okay. Hydra full error 1. The size of the tensor 401 must match the name of the tensor, or same size of the tensor at non-single to dimension 0. Okay, so it's trying to load something, and the size of the thing it's loading is not correct. So good thing we added this dash dash verbose. Now let's actually go through these lines and these logs here and see what's happening. best part about learning transformers and TIMM and lightning and flashing and everything is that they'll all be obsolete in 5 years. The field moves so quickly. Yeah. I 100% agree with you. There was like an equivalent one at Google that I had to learn to use called GenConfig, and it was just the same nonsense, just all this crap. And then there's also an experiment tracker. Why does that sound weird? But very similar to Dora. There's a similar kind of thing that you have to learn how to use. And then I went to work at Weights and Biases, which is its own experiment tracker. So the secret is all of them suck. None of them are good. Every single config management, every single experiment tracker or logger, all of them suck. World size is 1. Skipping init. All logs stored in there. Loading audio data split. So here it's actually finally getting the right audio data. AudioCraft solvers.builders. Getting pre-trained compression model. Okay, compression model has 4 code books with 400 cardinality and a frame rate of 25. Cool. No EMA on the model. Model size is 406 million parameters. Base memory usage is 6.51 gigabytes. That's pretty good. That means that you can fine-tune the small model with 6.1 GBs. I'm actually curious. We're going to get an error, but I'm curious how much usage the medium one has. Let's do that. So 6 gigs for the small model if you wanted to fine tune it. This one's going to CUDA out of memory, but hopefully it gives us that log where it tells us how much memory it would take. 29 gigs. Holy shit. I couldn't even train this on my other computer if I wanted to. How much is the big one? I'm curious. Large. All right, so we had 6 gigs to fine-tune the small one, 30 gigs to fine-tune the medium one, and tried to allocate. It just dies. It doesn't even tell you. It dies before it can even tell you. All right, let's go back to our small bear. Small bear, medium bear, large bear. So now let's go to the small bear. All right. Loading pre-train, ignoring load best and ignore state keys. Checkpointing is not the current load state dict from best state. Ignoring keys when loading best, and this isn't empty, so it didn't ignore any keys. Error executing job with overrides. Solver model LLM continue from conditioner text to music. All right, and specifically where it's failing here, it's failing flashy, flashy, flashy. Like, can you just tell me this tensor name, the name of this? Like, that would be so much easier. Let's see if we can do Hydra full air 1 at the beginning here as they're recommending. So you go up key. Let me make this a little bit bigger for you guys. And then I'm going to basically put this environment variable here. Oh my god. But I'm going to put this Hydra at the very beginning, Hydra full error 1, because here they're kind of recommending that it'll give me the full stack trace, so hopefully I can figure out which part of the model is erroring out here. Okay, so now that we have the full stack trace, self.states, AudioCraft utils best state, load state dict. Load checkpoint. So it's actually AudioCraft base, best state, MusicGen, load. Let's go to this exact file here. So let's go here. We copy the path to that. Then we can Control-Shift-P in here. Open up this. Specifically, we want line number 81. So we go to 81. It's right here. So this is where we're having issues here. So let's do good old-fashioned debugging there. I'm going to print that. I'm going to save it. And then hopefully it'll print out a bunch of these as it tries to load them. And then the last one that it prints out will be the one that we know we want. Okay. So let's see if we got some of them to print. None of them printed. Oh, here we go. They did print. So here's what we got. So loading blank, comma blank. So K is the key, and then name is the name of the state. I guess substate would have probably been more useful. Or no, name is the name of the substate. Okay, so we're loading the condition provider that has some conditioners. The conditioners have a description. The description, which is the text description of the audio file, has weights and biases for the projection of that. And then now it's trying to load the model embedding 0.weight. And that's where it's failing. So it's trying to load the wrong thing. You see it now here, the embedding is of dimension 2049, but it's trying to load weights that are of size 401. So why would it be loading the wrong weights? Well, we know it's in the conditioner, so maybe let's get rid of this conditioner here. Maybe that is what's causing the issue. Let's do that. Okay. No. Still fails there. Huh. Let's Control F here. If we Control Shift F inside the MusicGen config folder here, find in folder. Let's see if we can get 2048. Right, because it's failing here. It's saying 2049 and then 401. So 2048 is the number of RVQ bins. Okay, what about 400? Transformer language model card 400. Debug compression model. Let's try something crazy here. What if we do 2048? Okay, at least we got past that error, but now it's just like, dude, what the fuck are you talking about? Like, you just kind of nonsense this. Cardinalities of the LM and compression model don't match. LM cardinality is 2048 versus compression model cardinality is 400. Okay, so it's definitely this that's fucked up. But let's see. If we go to MusicGen base, Where is the transformer LM? AudioCast. Compression model checkpoint. Let's do this. Let's take the debug and let's change. Let's actually get rid of this and get rid of that. Put that in there. See what we get. All right. So basically what was happening is that the debug config for the MusicGen was using this debug compression model that basically is just a bunch of nonsense. So I went and I took the compression model checkpoint from the base config and put it into this debug config. Was able to load all of the stuff. So you see it printed out everything, loaded state dict, loaded the thing, and now where did it fail? Tried to allocate 20 megabytes already allocated. Okay, so we're running out of memory here. What is our memory currently at? It's currently not being used at all. Okay, so I think maybe part of the problem here is that we're using the medium one. This one, conditioner. Let's put that there. Now that we know it's not this. Okay. Loaded model hash. New pattern. Out of memory. This encodec 32 kilohertz is too big. What if we make the batch size smaller? Let's make the batch size 1. I feel like that should be cleaner. Or smaller, you know, decrease the batch size. Should hopefully not get CUDA out of memory errors. Still getting CUDA out of memory errors. Specifically the CUDA memory errors coming from this Atom W here, the Atom optimizer. Okay. Segment duration, let's do 1 second. Optimizer updates per epoch. Atom W. I don't think there's anything else we can do to the optimizer to make it smaller. Maybe let's try autocasting to float 16. So here it's autocast false, which means it might even be doing this at 32 kilohertz. So let's copy that. Or might be doing it as float 32. Kind of seems like it's still autocasted. Let's also get rid of the debug print that we put. So here in here we had a debug print. Let's get rid of that. We don't need that anymore. Let's close that. Still getting the out of memory? Yeah, still getting the out of memory. Okay. We're close though, you know, it wants to take a step. You see it's inside the run step function here. So it is actually very close to training. It's just failing out when it actually tries to run the optimizer and accumulate the gradient. So rather than messing with this debug config, let's actually go and create. Can I use bfloat 16? Maybe, I don't know. That's actually a good way to check if it even T5 will be evaluated with float 32. It kind of seems like it's not auto casting. You know, like here they say AudioCast D-type. We actually Control-Shift-F for this. When does this get used? Oh, actually, look at that. The other one's... It's only used here. Okay. Let's do this. So let's go to MusicGen. MusicGen. Let's do the bass. The bass config. Clear, paste. All right, so now let's try the bass config. And this is where we were getting this data source.evaluate crap. All right, but now we understand a little bit better, so maybe we can better understand what's going on here. So dataset batch size, let's make this 1. Sample on wait. Let's actually open this up on a side here so we can compare the debug config and the bass config, because we know the debug config was working. So audio default self MusicGen LM override audio example. See how this is different? Why don't we do this? Why don't we take this, put it here. So we're going to override the dataset with the example dataset, which is what happens in the debug config. Oh shit, guys, I think it's working. Can we even train this? CUDA out of memory. 9 gigabytes already allocated. Fuck. We might not even be able to train this. We're just too poor. Our GPUs are too small. Dataset size 1. Updates 1. EMA. Maybe if we get rid of the EMA, it'll cosine, learning rate schedule, log to Tensorboard. What can we save memory on? Specifically GPU memory. Fuck. I don't think there's very much we can save memory on. I thought we could be able to do this. What if we try X small? This might actually be the reason we were getting that error with the 400 trying to fit into the 2048. Yeah, your 23090s seem obsolete. I'm totally with you, man. I don't even have two 3090s. I just have one. So why don't we, here, let's go to this actual point where it's actually trying to solve it. So here in run epoch, solver.run, run epoch, right over here, line 571 in MusicGen. So let's go here, let's copy this path. Copy. We're going to Alt Tab in here. We're going to Control P. We're going to open up that exact file. Let's close. Can I like close out of this? So we're going to come here. I think it's Control Shift G, Control G. What's the Control G? It's the hotkey, and it's line 584, Control G 584. Okay, so here is where we're going. This is the train. start epoch super.train. So let's put a import PDB and a PDB.setTrace right here. And I want to see how much memory we have at this point, right? Because I'm curious, when we actually try to run this, it's going to load the model, and then when it actually does the training, that's when it'll probably start putting all the optimizer stuff into the GPU memory. So I want to see how much memory we even have before then. So if we move this here, let's just make this a little smaller, and let's run this. Okay. So it should hit that breakpoint. You see, look at this. You see it's going up, it's going up, going up. It's at 6, it's at 7. There we go. Okay, so just loading the model, it's at 7 gigs, which seems about right, because whenever we were doing inference earlier in the stream, we loaded the small model for inference and it was about 6 gigs, which is kind of roughly what we're seeing here. Maybe one thing that I'm seeing here is the EMA. So the EMA is, we actually have a stream where we went over EMA in detail, but it's basically a moving average of the weights for the purpose of stability. But I wonder if we get rid of the EMA, whether we'll have we'll use less memory. So let's try that. Let's try Control P music. Let's open up this config file again. Let's get rid of the EMA here. Generate batch EMA use. Let's do, oh shit, here you go. You don't even need, you can just do this. Let's do this, CPU. So rather than on the CUDA device, let's put it on the CPU. All right, so we put it on the CPU, and if it's on the CUDA device, it takes roughly 7 gigs. Let's see what it takes when we put it on the CPU. Initializing, there we go, look at that, way more manageable. All right, so the EMA, the moving average of the weights, is basically an extra 3 gigs. So if we put the EMA on the CPU, saves us some memory. Maybe now we can actually train. Oh no. All right, dude, I need to use my money to buy a A100. What is GPU A100? Can I just fucking buy one of these? 4 GPU, 20,000. I don't want to drop $20,000 on this. Fuck. 30,000 for an 8 box. Dude, I can do so many other things with $15,000. Can buy like an old used A100. Here we go. NVIDIA A100 7,800. That's still super expensive. That's not even the best. Like, you're gonna drop $10,000 on a GPU and it's not even the best. It's like a shitty one. That's no good. Or not shitty, but it's outdated. Go H100. Can I even buy these? I'm pretty sure you can. Can you even buy these as like a consumer? I don't know if you can. I think you need to know someone at NVIDIA to even be able to buy one of these. NVIDIA H100 GPU. It seems like maybe you could just buy it from dhooney.com. An 80 gigabyte H100 for Look at that. You saved $3,000. Totally worth it. Last time I checked, there's a significant difference in quality between the size of the models and AudioGen. Yeah, I can't even run the medium inference. Let me actually check. Okay, what else can we reduce here? So maybe if we get rid of the learning rate scheduler, we save a little bit there. This is probably not going to be on the GPU though, so I doubt that's really going to give us a ton. Maybe, what else? What else can we... Sample on weight, sample on duration, batch size 1. What if here, I think in the debug YAML, they were clipping the segment duration. Yeah, so what if we clip the segment duration down to like way smaller? Let's do this. Segment duration equals 1. See if that does anything. All right, we're at 2 gigabytes, 2 gigabytes, 4 gigabytes. Loading the model, come on. Okay, so 4 gigabytes so far. Okay, now we pray, hit continue. What are we at? 9, 11. Oh. Dude, we did it, guys. We did it. Look at that. It barely fits. 11 gigs out of 12. Holy shit. Okay, so we succeeded, and we had to do... So that not only is this already the smallest possible version, so this is the small model, but we also brought the batch size down from 4 to 1. We put the EMA on the CPU, and then now we decrease the duration of the audio, which you can basically think of it like the context length in like an LLM, right? So the bigger your sequence is, the more memory it's going to take. So if you just decrease the size of the sequence, it's going to be the easiest way to make the memory smaller. So we're decreasing the segment duration to 1. I think you don't know what the default is. I'm guessing the default is 5 seconds, because that's what the other one had. But look at that. Look at that. We did it. All right, so now we're running into some bullshit. What are we running into here? Called synchronous. Okay, these aren't even errors. These are warnings. And look at that. We got 1. We trained it. It was just training this whole time. We trained 1 epoch. Not even 1 epoch. We trained 200 out of 2,000 steps, because we did read earlier on the stream that they just arbitrarily decide that 1 epoch is 2,000 steps rather than 1 epoch being exactly whatever the size of your data set is. About 2.4 iterations per second. So 200 training steps took about 10 seconds. Learning rate of 2.5 e to the negative 2. That's kind of a big learning rate. Probably want something a little bit smaller than that. Grad norm, nan. That's not good. Get a nan on the norm for the gradient. Maybe it's just because it's the first step. PPL, this perplexity. Okay, that seems fine. I think there's probably a warm-up period. Dude, the warm-up period is 4,000 steps. Dude, what? Let's make the warm-up period 100 steps. Lead times are crazy. Maybe let's fund one of these startups you were talking about yesterday to collect some money or create a meme coin. Yeah, dude, that's what we need. We need meme coins. Hobo inference wins again. We did it, guys. Completely meaningless. Okay, let's also... there's no way we're going to get through 500 epochs here, so let's just do 400 epochs, or 200 epochs. So we're going to do 200 epochs. Or no, not even, this is fucking epochs. We just need one epoch. And we also need to change the number of steps per epoch. So I think they mentioned that in their documentation, right? Somewhere over here. Yeah. Optim.updates per epoch. Okay, so this is what we need to change. It's currently at 2,000, and that's going to take way too long. So let's come back here. So close this. Optim epochs 1, but we also want updates per epoch. Let's just say 200. So 200 steps is going to be 1 epoch. We're only going to train for 1 epoch, and we're going to do a warm-up of 100. And it seems like log Tensorboard is true, so do they even have it running? Tensorboard, come on. Site can't be reached. Where is the log dir? Let's Control C out of this. Clear. Exit. Control D. Okay, so now that we finished debugging, where did we actually put this trace? We put it right here. We don't need it anymore. Control W out of that. And this is dumping log files somewhere. I feel like it should tell us where it's dumping the log files. Loading audio. All XP logs are stored here. Okay, so temp AudioCraft oop. Let's look at that. Do Nautilus, and Nautilus is the Ubuntu Linux file explorer. So okay, what do we got here? We got arrays, XPs, folder is empty. Oh, here we go, Tensorboard. All right, so if we point Tensorboard to this path right here, so we can say let's just Control C out of that. Temp AudioCraft oop. Let's do open up a new terminal here. Let's make sure we activate our AudioCraft. AudioCraft. Make this big so you guys can see. And we're going to say Tensorboard -- logdir, and then we're going to point it to this file here. AudioCraft oop. Copy. Put that there. No module named NumPy. Pip install NumPy. How the fuck does this not have NumPy? What? What the fuck is going on? Tensorboard is failing under a no module named NumPy? What the fuck? On to activate base. Base pip install NumPy. Pip install Tensorboard X. What? Python import NumPy. What the fuck? Let's go celebrate with some alien invasion sounds. Tensorboard no NumPy. Pip3 install NumPy. Pretty sure that's what I did. Dude, that is wild. Okay. I think there's a Tensorboard extension for Tensorboard. No. Let's just copy this entire thing here and blast our good old buddy ChatGPT with this. New chat. Blast you with this error. Let's see what it says. Yeah, I mean, I could have told you that. So what this Tensorboard is using this Python here. So if we actually run this Python, which Python? Yeah, so you see it's using the mini conda Python. So I need to change how to change the Python that is used by Tensorboard. Which Python 3, attach, activate the Python environment, install Tensorboard. I've already done all this. Verify installation, already done that. Which Tensorboard? Help. Help me. Pip install Tensorboard. Oh my god, we're not going to have... I'm about 3 seconds away from saying fuck this. Let's copy with the thing already there. I'm getting distracted. I'm sitting here debugging Tensorboard dependency issues rather than actually... Tensorboard is installed. It's using the wrong Tensorboard. Uninstall the local user's Tensorboard, activate the miniconda environment, and then use Tensorboard. All right. Yes. Okay, now conda activate AudioCraft. And now, can we do this? Pip install Tensorboard. Bam. All right. Damn, that was really weird. That was annoying and weird. All right. Now we're on Tensorboard. Time series. Here we go. Here's all the data we have so far. We've run it a couple times, though, so this is a little weird. So why don't we just delete all this crap? So let's open up a new terminal here, and we're going to do our good old Nautilus. And what is this file again? Boom, boom. It is -temp AudioCraft oop. Let's go there. Open that up. XPS. I don't think we need any of these, so let's just delete all of this. Okay. So if we refresh here, should be empty. Yep, okay. So we've cleared out all the Tensorboard data. Now let's go back to what we were originally trying to do, which is tune this. Okay. So we were tuning this. We changed the number of epochs. We changed the number of updates per epoch. We changed the warm-up. And let's run it. See what we get. All right. It's loaded successfully. It's doing its thing. It's training. While that's doing that, let's open up. Actually, why don't we do this so you can see a little bit better? So now you see the epoch is only 200 training steps, but it's still going to take a second because our computer's really slow. Control T, W, Control Shift E, Control Shift G. That's the one we want. Let's see, what do we change here? Get rid of that. What do we change here in the fine-tune script? Why don't we just copy the one that we need, which is, I'm just cleaning up my GitHub, you know, I just want to be able to make a little commit that's clean. And this thing here, this is the open containing folder. MusicGen is ready right here. That's not what I want. I want this one, and I'm going to rename this. I'm going to copy, and I'm going to paste it. I'm going to call it MusicGen Bass 32 kilohertz jank. And this is going to be ours. So that means we can go ahead and undo all the changes here, discard changes, discard any changes here. And for this debug.yaml, we also don't really want to fuck with anything there, so let's discard those. And here in the fine tune, let's just get rid of the large and medium and only keep the small. And we want to use the bass underscore 32 kilohertz jank. Okay, so we should be good to go. Let's see, it was training. It finished that one epoch. Now, after it finished the training, it's going to run the validation. So validation is a separate data set from the training data set. And the whole point is that it looks different than your train. It's not the same exact data, so you can evaluate or validate that your model is correctly learning something and not just memorizing your data. But first thing I notice here, you see how the validation, one epoch of validation is 10,000 steps, and we don't have that amount of time. Ain't nobody got that amount of time, so we're gonna have to reduce the amount of validation steps here. Or maybe not, you know, this actually seems like each step of validation is much faster. You see this 33 iterations per second versus training, you're at 2.4 iterations per second. And actually, why don't we refresh here on our Tensorboard? We got some plots, right? So we've only trained one epoch, so kind of it just looks like little dots because there's only one thing. But let's see, maybe you can make this one big. Let's see what we got here. We've got just 1 point H params. What H params do we have? Device, AudioCast type, seed, 2036, solver, parallel coordinates view. Here's your different data sets. Data source.evaluate, data source.generate. So if you wanted to fine tune on your own custom data set, all you have to do is replace their example data set. So they do provide one example data set here. In data set, this one here. So if you just basically copy this. So actually, why don't we try to add our own example to this. Actually, if we copy that, paste, let's call it Electro 3. call this electro 3. And let's see. Artist. Baboo. Sample rate 48,000. File extension MP3. Description. Baboo's favorite song. Keywords. Awesome. Cat-tastic. Name electro 3. Okay, so I mean, obviously I'm just kind of doing this to see if we can actually get it to train or whether it fails out. Okay, we're almost done with the validation here though, so let us finish this out. Let this validation finish out, and then it might go straight into eval after that. Maybe that would be my guess. I should also turn this learning rate down. Optimizer learning rate of 1. That's not what we want. We want 1E negative 6. It's a better learning rate. All right. So it finished the validation. Then it went to evaluate. And when it tried to evaluate, error executing job. So when it tried to run the eval, what did it run into here? Maximum size is 8,000, but size is 12,800. Okay, so the waveform that it consumed for the evaluation is too big. Probably because we changed this parameter here. The segment duration. Let's see if we can get it to work like this. Fine tune. Sudo chmod plus x finetune.sh. Give it permission to run so that we can just do that. That's basically just the commands that we have had this entire time, but I just put it inside a little script so that we can edit it. It's nice and clean. What are your workstation specs? So this is a Linux computer running Ubuntu 22.04 with a 3060 GPU that has 12 gigs of memory, running CUDA version 11.7, cuDNN 8.5, and then yeah, I think that's pretty much it. If you're also interested, LS CPU, that's the CPU. So it's an AMD Ryzen 9 12-core processor. And then if you do LSMEM, this is the memory. So I have 66 gigs of total RAM, which is a lot. More RAM than I have GPU memory, sometimes also called VRAM. So maybe not the best deep learning rig. Okay, so now we successfully were able to run it with the config file that we created. Now you see that we're using a much smaller learning rate. And, oh, I see. Okay, so I was confused. I was like, why do they have a learning rate of 1? And the reason they have a learning rate of 1 is because they are, that's the starting point for this learning rate scheduler. So you can see here how the learning rate scheduler just kind of immediately brought it all the way back down but it's a cosine learning rate scheduler. So you see how it's going. It goes from 3 to 5 to 7 to 9, then back down to 7, back down to 5, back down to 3. So it's cosine learning rate schedule goes up and down. This is what the learning rate looks like. So you're going down and then back up and then down and then back up. I think it's a little bit more smooth. It's not as peaky as that one, but I still don't like these nans here and these inf here. It's not good. Maybe let's see if we can change the amount of validation that's going on here. Evaluate, generate. Can I change the validation? Dataset audio. Audio caps. There's probably a config somewhere for solver, MusicGen, evaluation, objective eval. Max audio duration, num samples. These are probably what we need to change, right? If you remember the last error we got. And then we could probably turn off some of these metrics here, because I think some of these metrics are going to cause issues. I'm just starting my CS with AI ML course in college next month and was looking for a laptop. Yeah, I don't know, if you're buying a laptop, there's a lot of different things to consider, right? So if you work, most tech companies and startups will use MacBooks. So I know MacBooks are really popular right now. There's a bunch of people who actually do inference with the MacBook chips. That's like a whole community and sphere of machine learning that you could get into. Unfortunately, of course, MacBooks are expensive, so maybe if you're a college student, you probably can't buy yourself a MacBook. When I was in college, I used a laptop, a ThinkPad, one of these, and I had a dual booted. So I had it dual boot Windows and Linux. So the Linux distro that I use here, this is Ubuntu. This one's free, heavily recommended, been a user for a very long time. And I would use this, and then I would dual boot it, which means that you're installing both operating systems. And so that if I wanted to play video games with my friends in college, I could turn off my computer, turn it back on into Windows mode, and then play games with them. I just bought an M2 32 gigs. Yeah, Macs are just great. Like, people, they just keep getting better. MacBook. Let's see. MacBook Pro. 14-inch, 16-inch. What kind of specs can you get with this? So there's different chips here, M2 Pro, and then M2 Max. Okay, so it basically seems like the GPU got twice as many, almost not twice as many, but like significantly more cores on this M2 Max. Twice as much RAM, and then 1 terabyte solid state disk, which is just fucking gnarly. I remember back in the day, like 1 terabyte still seems extreme to me, but I know nowadays that that's pretty standard. This is a fucking monster computer, and I could have it within 2 hours. Oh, they have a different GPU for this size? That's weird. Interesting. Okay. I can't upgrade the RAM later, and I don't have money for large RAM. I don't think you really need to upgrade the RAM, to be honest. I've obviously done that, you know, putting new RAM sticks in a laptop before, and when you have a workstation, you put new RAM sticks all the time, but I think you're just going to get a new computer. Like, if you get to the point where you want to put more RAM in it, the GPUs have probably increased a couple generations, and you're just going to buy something new for the GPU, right? At this point, the processor, the RAM, which is just the normal memory, the size of your hard disk, like those aren't the limiting factors anymore. It feels like for the past 5 years, it's like the limiting factor always ends up being the GPU. Basically, the reason I'm buying something new 2 years from now is because the GPUs have just gotten 10x better. But I feel like all the other stats are kind of, it feels like they're kind of like capped out at this point. They don't really, really matter. Okay, what are we at here? So we only have one epoch right now, so why don't we try 2 epochs? Let's change the updates per epoch to 10, and then let's do 10 epochs. And let's turn off, how do I turn off the override deset? Can I turn off the validation? Top K, strategy, sample, override deset. How would this compare to an A100, H100? H100 and A100 are monstrous. So those are going to have way more everything than the Apple chips. You're not going to realistically train anything on an Apple chip. You're probably going to be able to fine tune things on an Apple computer, on a little MacBook, but you're not going to be able to train anything from scratch. But then you could also argue that we're kind of in a phase of machine learning where you're never going to train anything from scratch anyways, right? Because 5-10 years ago, you could actually train things from scratch on your computer and they would actually be usable. But now you're almost never training anything from scratch because you need so much compute, so much time that somebody else is training it from scratch on their cloud servers with their giant budget, and then you're taking the already trained model and just fine-tuning it a little bit more. So in terms of performance, the H100 is going to be way better. A100 and H100. If you spend $15,000 on an A100 and then another $5,000 on all the extra stuff, like it's going to be less than $5,000, but the CPU and the motherboard and the power supply and all of that computer is going to be way more powerful than the M2. But it's a completely different class, right? It's like you're kind of comparing the horsepower of like a tank with the horsepower of a car. Like the whole point of the MacBook is that it's very small and very clean and minimal, and you can use it. It's like a daily driver. MusicGen evaluation. Can I add this in here? I'm trying to see if I can turn off this validation. Validation. Rerun the value if key equals valid. See if I can find it. Validation. Actually, that's not the one I want. Don't save. Validation. Updates per epoch, something like that. It's gonna for sure fail, but let's see if that even runs. All right, so now comes the validation. Here, that was that quick little train. Now it's going to try to validate. See if we actually managed to change something. I just literally guessed at this config value. I have no idea what the validation config is called. I just guessed that it maybe has the same style as the train one, but it's just all a guess. No, it looks like it died. Oh, no, look at that. Okay. Let's maybe search for valid. If valid field, key, BPM, genre, keywords, valid, none, valid step, maxed step. Looking for, here we go, num samples valid, dataset.valid.num samples. It's not what we want though. Indicating valid. I want to turn off validation. Return train valid. Here we go. Valid everyone. What if we change this to valid? Maybe we could just do valid null. Let's see if that works. Just fucking configs. This is not the right config. This is sound 16K, music caps 32K, max sample rate. Yeah, these aren't the same. Okay. Whatever. That's fine. I think we mostly got what we wanted. Meaningless training for a meaningless purpose. But the final goal is not the destination, it's the process of getting there. And in the process of getting there, we kind of learned about this repo a little bit. So I think I'm just going to leave it there because I can hear my child crying in the background. So let me commit these two things here, the fine tune and the MusicGen sample janky, and say janky training. Okay. Okay, cancel. Seems fine. And let's make sure that we can see it, so at least you guys have access to this profile. Maybe my child would like the lullaby, probably not. Child's gonna be scared of the lullaby. Where did I put that? AudioCraft. And then we look at the commits. No, did not. And then we need to sync these changes. All right, there we go. All right, there we go. Janky training is there. Okay, so if you guys want to continue on from here, feel free to check out this forked repo. If not, totally understandable. You probably need to do this on a much bigger computer. That's immediately what we ran into. We just ended up doing a bunch of hacks to make it work on this smaller computer that I'm currently on, but those hacks are also going to make the result not as good, right? So if you push gradients with a batch size of 1, it's going to be a very kind of noisy, shitty signal. You definitely want more more samples within your batch, so that, or just a larger batch size to get a better gradient direction. But other than that, that's that. I got a blast. Thanks for hanging out. Hopefully that was kind of cool. Let me know if you guys are interested in any other papers, and see you guys later.